Bon, bonjour et aux excuses pour les problèmes techniques. Je suis très honoré d'accueillir ici le professeur Ignacio Ciampiti, professeur Farming System au département d'agronomie de Kansas State University, avec lequel nous avons collaboré depuis 2 ou 3 ans et qui fait une visite en France pour essayer de nouer des collaborations entre les États-Unis et la France sur le problème du management, de la conduite de la fertilisation azotée des cultures et aussi des progrès, de l'estimation des progrès génétiques et de l'amélioration des plantes en vue d'améliorer l'efficience d'utilisation de l'azote. Donc, bienvenue à toi, Ignacio, et je te laisse la parole. Tu vas présenter un peu ton groupe de travail et les recherches que tu es en train de mener. Merci.
Okay, thanks, Gilles, for the presentation, and for sure it's a pleasure to have the opportunity to share some of the things that we have been collaborating for the last almost, I say, more than 10 years, and then for sure the last 5 years we intensify more some of this exchange of ideas. We are familiar with Zoom, so most of the collaborations and meetings that we have done were via Zoom, so it's good to finally be in person. So the idea of today's presentation is I would like to give a brief summary of some of the things that we worked in the past and trying to discuss a little bit about ideas for the future. I first will start introducing a little bit the topic. So we'll go a little bit about telling how is the way that I work with my team. And then after that, I would like to discuss the problem of nitrogen. So, and I would like to introduce a new concept that we are working on, why we need to start discussing on nitrogen. And nitrogen is still something that is being big puzzle for many crops, and specifically when you look at the US for maize. Believe it or not, the nitrogen nutrition index is still something that is not yet well used, although it's really well understood, and there is a lot of literature. If you start thinking and looking at the literature, most of the information, and I will say probably the best publications are coming from France, but when you look at the rest of the world, there are still very few, researchers and people adapting and using this concept. And then finally, we will enter into the idea of discussing on breeding for natural use efficiency and how we need to start thinking about changing this framework, and conclude with the idea of this. One of the main points of my visit is to start seeing if we can expand our collaborations, and in order to do that, we establish this global database on nitrogen nutrition index. So let's go quickly to the team. So I'm very fortunate to have an excellent group of people, and then, that's the key of the success. When someone is asking me, that's a secret. We have many PhD students. I'm very lucky to have one of the PhD students here with me, Josefina, that is working with in collaboration in an exchange with Dr. Makowski, and so she will stay here in Paris for close to a month, working on some of the Bayesian model for nitrogen nutrition index and the critical dilution curves. And then we have several master students and a few postdocs. So it's a very large research team and working on many multiple topics. So you will see just in a few seconds. So some of the areas that we are working is we are really looking at crop physiology as our basis and foundation. Okay, it's the foundation of trying to understand the process in the plant, and from there we start upscaling to crop modeling, to remote sensing. We also focus on analytical methods because we work on carbohydrates. In analyzing the plants, we work on fixation for legumes. And we do a lot of extension. So the US system is a little bit different than here in France. So the US system has three-way appointments. It's research, teaching, and extension. In my case, my appointment is mainly on research and extension. So we tend to do and work with farmers. And then another thing that is just close to my heart too is this consortium that we established 2 years, that we're doing some work in Africa and Asia. So, and just to showcase some of these topics. This is the consortium, so I'm the director, but we have many people, many faculty, and many multiple students, PhD and postdocs. And our work is, we're trying to develop some digital solutions. For example, even looking at best management, or best management using National Nutrition Index in Senegal and Bangladesh and Cambodia. So these are the 3 countries. So that was a little bit about the team. I will jump quickly to the research. So, but before we do that, I want to make sure that I show a little bit about what is a little bit the secret for the success, if I want to share with some young people. So for me, it's important to have personal connection to the students. I believe that active mentoring is relevant. And in fact, some of the collaborations that we established with Gilles is an example of even still the type of mentoring that Gilles does with many young people. So, and I'm one of the examples here. Communication cooperation. So we try to discuss with my students that we don't work alone. That's a critical aspect. We work as a team. And I think working in collaboration and connecting research is critical. As I mentioned, extension is critical for us. So we work with farmers. We listen to farmers. We try to, in many situations, many of the new questions are coming from farmers. They have questions about how late should I apply the nitrogen? Should I split the nitrogen? And then we start thinking about those questions and find ways to address those. And then I believe on this concept is in many situations, achievements and awards done on myself, I mean, are not that important as any awards or professional development coming from my students. So yeah, that's the legacy that we have. So I believe on this concept, and then also believe in the idea of training new people, leaders, and hopefully in many situations when close or before they finish the PhD, in many situations they become much better than the advisor. That's the goal. What is the idea of this traditional versus quantitative agronomy? Let me start with traditional agronomy has been around for many years, in fact, maybe a century. If you think about the way that we talk about topics in agronomy, we usually discuss about field experiments. And then another team does the economic analysis, and another team does the crop modeling, another team does the remote sensing. And in the last couple of years, this mentality has shifted. And we start seeing maybe in the last decade, more and more people start connecting and trying to integrate concepts. Going all the way from a study that we do in a growth chamber or in a greenhouse and upscaling to the field, and then using a crop model, to look at basically how these responses are becoming more universal. And this is a concept of this quantitative agronomy. And I try to call quantitative because I think that we tend to undersell all the great work that we do. And I think that in many situations, we talk to people, to farmers, and we just mention a number. We kind of undermine all the science, the great science that we do together. And the idea of quantitative means that all these aspects, they need to work together. So we need to find ways that we work together with how we can think an idea from the field and take it all the way to a decision. So the farmers will have the chance to implement and make a change, take an action. So, and in order to do that, in many situations, the field data is our foundation, but we need to integrate this field data with crop modeling and remote sensing into a decision support tool. And this is the concept of this idea of integration. To give you an example, even today, in the US, we are still recommending plant density for maize that is usually coming from experience. When I have a call from a farmer, they're asking me, what is the optimal plant density for my field? I start the conversation giving a nice speech, but at the end of the day, before the farmer goes out, he's asking me again, what number? Tell me the number. And this is a problem because we become professionals that we do science, but then at the end of the day, we are basically providing a number. And then we need to start thinking about how we can start changing that mentality. It will take us a few decades. I have more hope on the people that's coming after me. And I think that is coming on the idea of, let's start thinking about probabilities. I always give the example of, and it's an easy example, when you look at the weather channels. In the US, those weather channels are very popular. And they tell you, tomorrow there is a probability of rain, and it's a 50% probability. They never tell you, tomorrow will be raining. And then the question is how we start thinking on this direction, how we start offering the person on the other side a probability and the best probabilities, and maybe different scenarios of probabilities. And then Josefina is one example here. So she's implementing, working on these concepts, and we need to train different people. And that's a challenge that we will have, because today we need to refocus our training. And I'm happy to see that another student that is here in the room is also working on this direction. So, I mean, integrating data from the field, from growth chamber, in crowd modeling, and trying to think about decisions, no? And I think that that's a main factor, a main example that I'm showing on this slide is like, to take a decision and to provide a probability is not only just to do a study and to provide the foundation of that study, but integrate data from different sources to develop a model, to develop a predictive model that has a probability. And that's exactly where we need to start, the direction that we need to take to move on this way. To give an example, I think that the main and easy example is with nitrogen. I think that in the US, we have been working with nitrogen since probably 1800s. And I don't feel that we are too close to solve this problem. And there has been a lot of investment. If you look at the last 100 years, we tried to do a calculation of the amount of funds invested on nitrogen topics. And I think that is close to more than $1,000 million. So, and it's nothing that has been solved yet or got close to be solved. And some of the main problems is because we have this issue of what I call circularity. Circularity means that in many situations, we go in circles and we try to go back to the same point. And we define an NUE coefficient, yield divided N uptake. And now we try to improve the coefficient to say, no, now I will use a differential NUE coefficient. And then we always go back to these calculations that are very trivial because they are not going back to a process. They go back just to two outputs. And here's an example. Today, we still, many of soil fertility, we still are using this response, maize yield, different nitrogen supply. So you have your B0, which is a situation we don't apply any fertilizer. That's a yield at this point. Then you have a response, which is basically the NFE, which is the efficiency of response per unit of fertilizer. And then we have this yield, which is the economic optimal nitrogen rate, no? But if we are honest, if you look at the graph on the right, this is exactly what is going on. It's not just one slope or one equation or one model. And sometimes it's funny to see many discussions in this topic that they talk about the models. Is a linear plateau or is a quadratic? And still are going with that direction. What is the best model to represent this very complex process? In fact, if you look at the graph, if you look at all the years and all the variability in the years, there is no one model in many situations. There are many, many models, and we need to define what are the probabilities that one model will occur and will occur with different, basically, weather scenarios. And that's exactly why we cannot solve the nitrogen problem, because we have a large uncertainty. From now on, we will discuss uncertainty as one term that basically will give us some idea what is the range for the estimate. Okay, so if my estimate is soil nitrogen supply, in many situations we see that for us, this uncertainty on trying to make an estimation of the soil nitrogen supply, so the yield when with maize is not fertilized. In many situations, we have a deviation or a departure that is close to 40 pounds, I mean 45 kilos of nitrogen per hectare. So, and many of these is largely depending on the weather. If you look at the uncertainty chart, the radial chart, it shows that in many situations, 90%, yes, 90% of that uncertainty is based on weather, okay? And in many situations, it's based on the weather around flowering time or the weather around before flowering. And the questions are, why we go back to applying nitrogen at planting, and we still do that, knowing that we have a probability that most likely that number is wrong. Okay, and it's wrong because we have the weather that we don't know the weather. We don't never know the weather that will happen and will occur in the next 3 months. And this is an example of uncertainty. So another PhD student, we have a publication that we look at more than 4 decades, close to 5 decades of data. Look at all the different curves. This is the same location, and this is the yield response to nitrogen rates. And each curve is a different year. So now tell me which one is the optimal. And not only that, I mean, because uncertainty is not only based on the year. Here we say that the agronomic optimum is close to 150, but then the real optimum ranges from 100 to 200, which basically depends on the soil supply. And of course, depends on the precipitation and temperature during the growing season. So these, if you look at all the years, they're all different. No years are repeated, and then most of the variability is coming from there. But not only between years, also within the year. Even when we do replication studies, we get to find this, that in many situations we have even variability within the same year. So how are we planning to solve that? And that's one of the main questions that we're trying to think about when we discuss about nitrogen nutrition index. And again, look at the variability that we have within only 1 year on calculating that optimum nitrogen for maize. And not only that, that this year it has becoming a bigger problem. Why? Because the fertilizer prices are going up to the roof. And then the problem is that if you look at the grain price, maize is going up, but the fertilizer price is going up much larger. And then now we have a problem that in many situations I would say, have work on developing a maize or hybrids that they really are high productivity, but high depending on technology, high depending on the fertilization. And now the question is, what happens if you don't fertilize it? And here is all the problem that we face. So we talk about the model, we talk about the different response models of yield, nitrogen rates, and then we start discussing a little bit about this, that is Bayesian frameworks. There are many discussions about non-informative priors or informative priors. And I will let that Josefina lead that maybe questions, I mean, but I think that she's working on that, and that's the main point of thinking about how we can improve these models. The main message on this slide is like everything has an uncertainty, and even every variable that we look at the model has a probability distribution. So it's not just a number, okay? Once we start moving away from the idea of thinking on a number, and then I think that we start thinking about how we solve this problem. And the way that we will be solving this problem is when we start understanding the variability. And then just to give you an example, we did a study, for me was extremely interesting because we say, can we predict the yields using thousands of studies for maize without fertilization? So here you have in the upper section figure the yield for maize without fertilization. And you see that the predictions, I mean, even we can make predictions like in many situations during the spring with the spring weather, and you can have very good predictions on the estimate. But we also look at the uncertainty. So it's not easy to say, okay, I can predict the estimate, and then what is the uncertainty? And then can I predict that uncertainty? And if you look at the lower panel, it shows that the prediction of uncertainty is not as good as we have the prediction of the estimate. And similar is when we try to predict the maximum yield for maize. So the maximum yield, we can predict it quite well using, again, spring weather. But when we look at the uncertainty around that number, the uncertainty usually is very large, okay? And the prediction is not that good. So we have a high degree of agreement on the estimate, but really poorly predicted uncertainty. And the same was for the maximum yield, okay? And many times when we go back to these radial plots, we know that uncertainty depends on the weather mainly, okay? And usually the weather during the season, that's the main point. On the estimate, you will see that to calculate and look at the main factors affecting the estimate, the management, the soil, the weather, they all share a similar proportion. When you look at uncertainty, mainly everything comes from weather. Similar is when you look at the maximum yield for maize. The previous crop was also a really good factor. So if the previous crop was a legume, we had more nitrogen coming from that legume, so that was something that it was helping us to decrease the uncertainty. But every time that we were coming from soybeans, I'm saying legumes except soybeans, of course. I'm talking more about alfalfa, lucerne. But every time that we were coming from soybeans or maize, we have very little nitrogen, and then the uncertainty in many cases it increased because it was not really a good prediction in those situations. So this is what we put together. So these are all the studies that we collected for maize, and if you look at all the studies that they have no fertilization, so what we call the check plots. So here is a relationship between the uptake of the plant and the yields without nitrogen. And if you look at that relationship, basically it tells you that in many situations, soil and supply is a big factor. And then in many situations, if you think about the variability, you can have a large range of nitrogen and variability coming from the soil. So we need to also emphasize this point of how we can start investing more resources on trying to understand the supply of nitrogen, because that's another key factor to integrate into the nitrogen nutrition index. And as I mentioned before, when we were looking predictions of yields without fertilization, if we were using the entire weather of the season, we can make an excellent prediction. But when we use no weather, so basically before or at planting, those predictions are really poor. The spring weather basically was using 30 days of the weather of the first month after planting. So there are some probabilities that we can start thinking about how we can develop some decision tools of applying nitrogen, also integrating, for example, the current nitrogen nutrition index with expected weather forecast and soil conditions. And this is the problem with the soil, that we have still a large uncertainty on the amount of nitrogen that is coming from the soil. So now let's try to shift a little bit, and then let's focus on the problem. How do we solve this problem? If you think about the nitrogen nutrition index, and if you think about the emphasis, I went back a couple of years ago and I started looking to the research and the literature. And you will be impressed that in most of the literature, when people discuss about nitrogen, we have 100 times more studies looking at nitrogen use efficiency than looking at nitrogen nutrition index. Okay, and maybe if I look today, it might be more than 100, which basically is telling us that for many researchers, nitrogen use efficiency is simple. It can be calculated like this. I just have different equations. I'm presenting the most common. You can take NUE as a part of the yield, divide N uptake or N fertilization application, and you can divide in multiple components if you want. You can look at the first one, the recovery efficiency, how much fertilizer you recover as a part of your uptake. You can look at the conversion, how well you convert this uptake into biomass. And then you can look at this last factor, that is efficiency, the utilization and conversion of biomass into yield. So if you think about NUE, as basically proposed in the 80s, this ability of capturing nitrogen, using that nitrogen for biomass, and then allocating that nitrogen to the yield formation. Seems pretty simple, right? But the challenge is that it's not as simple. I mean, the main problem that we have is that we are taking two outputs, yield, and we're taking the nitrogen fertilizer, and we are making a ratio. And we understand that the processes in the plants are not just simple calculation of a ratio. So in many situations, I mean, even looking at the first studies from Plenet and LEMAIRE, what we always, I mean, there was a discussion there of the proportionality of an uptake to biomass and why it's not proportional to biomass. And today we know that if it was a strict proportionality, that will lead to a constant concentration in the plant, but that is not the case. We know that the main reason is, in many situations, the canopies cannot maintain this concentration or homeostasis. And in many situations, competition is one of the big factors. When we have competition for light, the plants are investing more in structural tissues that they have low nitrogen concentration relative to metabolic tissues. And we know that the accumulation of biomass, it drives, I mean, these two factors, the recovery and the conversion, no? If you look at this log-log ratio of uptake and biomass and the different nitrogen nutrition index, it explains quite well that in many situations, when we compare things, and this happens a lot when breeding programs, we compare different things and we say, okay, this genotype has much better NUE than this one. In many situations, we are not comparing those at the same biomass. We're comparing one genotype that has larger biomass, and in that case, we'll have higher conversion efficiency. And then when we wanted to make comparison across species, we need to emphasize the point that needs to be done at similar crop mass. And this is one of the issues why, in many situations, integration of NNI into breeding programs is a challenge, because it's easier to just calculate yield and the fertilizer amount applied, and it's really hard to obtain what is the NNI or the planting status at different points in the season. And again, if we look at, and I'm refreshing the idea of the concept of the dilution, here is what has been proposed by Plenet and LEMAIRE using the maize data set and looking at different fertilizer rates and looking at this linear plateau adjust on these different fertilizer rates. We are plotting the N concentration in biomass, so the N concentration of a plant dilutes over time, specifically until the moment of flowering or early milk stage for silage. And this is the way that we start defining this dilution. And then the questions that we have in the past were, are the curves universal? I mean, do we have one generic curve for maize across the globe? Is the curve or the sensitivity of the model fitting changing when you have different biomass or when you have studies that they don't have probably good quality data? And then we have started working in the last years with Gilles on thinking about these ideas, okay? Thinking about the points that we have some studies in the literature today that they use NNI and they fit critical nitrogen curves. But the problem is some of the data lacks sufficient information on how to feed that plateau, okay? So as mentioned before, Josefina, one of the PhD students working on this, she's working on doing some simulation studies, trying to understand what happens on the situations that we have data sets that we reach the plateau, how many times we reach the plateau, and what happens, for example, in the case of A on this graph, we reach the plateau, we have 4 fertilizer and rates. In the case B, the plateau we cannot identify too well because we only have 3 fertilizer rates, and you see that is increasing the concentration with biomass. And then the last one, we are not sure exactly because it's unidentified, but in this case is with a minimum of 3 fertilizer rates. So in many situations, the 3 fertilizer rate seems to be the minimum, and we will discuss at the end of the presentation on that. And it seems to be that if we can reach the plateau, like what we are seeing on the last panel, then we will have good quality data set to feed a critical model. But we have problems. In many situations, the quality of the data changes. And in many cases here, we show a study that we look at 12 SQ, and we change the range of biomass. And we have 4 conditions here, situations where data came from low biomass or from high biomass. And then in the lower panels, we have situations where basically the range of end supply was for non-limiting nitrogen. So if you look at the examples, in the first one, we have very narrow, low crop biomass. So really hard to define this dilution or the plateau model, the plateau section of high biomass. In the second one, we have very dispersed data sets and high crop biomass levels. So for the model, it's quite impossible to really work on the dilution and fit the dilution. In the lower panels, we have low number of data in the non-limiting nitrogen concentration. So we have problems basically of having this determination of this plateau. And then the last one probably is where we connect all the data and we have high number of data in the non-limiting conditions. And you see that then the uncertainty of the models is much smaller and reduced when you're looking at the entire data set versus the other 3 situations. So we will continue working on this and discussing more about this point. We have another study that we conducted, I think that was 2 years ago, looking at the universality of the dilution curves. So for that reason, we did a review analysis on different maize data sets. These data sets came from different sections of the world, US, Canada, France, Germany, and China. And then our main goal was to say, can we confirm that is one unique curve for maize? And in many situations, I mean, looking at this data and looking at the different hybrids on the literature, now that we are able to estimate uncertainty, we can confirm that in this review, we are suggesting that in many of the scenarios, a universal dilution curve seems to be the most appropriate. But there is always something that is an exception to the rule. When we start discussing about wheat competition, like one example here, or when we start discussing about changes in the canopy architecture for maize, for example, in the US today, there are a few companies that are starting to look at this short corn. So for this type of new hybrids or these short corn hybrids, that the canopy architecture is changing. So then we need to start thinking about this and re-evaluating the dilution curves. Mainly because it's partitioning of biomass and nitrogen to different leaf and stem organs. And we confirm, not only did we confirm that the data set for maize is universal, I mean, if we look at the data from Plenel and Lemaire, so we still are using those data just as a benchmark, and it shows in many situations that there is very minimum deviation when we look at universal model, a model using all the data versus the model fitted by Plenel and Lemaire. And then in this situation, we not only look at the model, but we also estimate the NNI from our curves, the universal curve, and we compare it to independent data sets from different studies. And still, we tend to see the same, that everything fits very well. So we are not seeing too much deviation on the dilution. So, and imagine that this reference curve was derived from, I think that was 5 or more studies located in France. And then we did that independent analysis on the second panel just to make sure that we were evaluating NNI and computing NNI in 2 different ways. We have different metrics. I mean, we can discuss on those metrics. I mean, but just basically confirm that the data set is very similar to the well-established curve. I mean, and continue to that, we also start asking some questions, maybe 2 big questions. I'm not sure if we have answers yet to that. But we start wondering what happens if we have grasses, different grasses, that they have similar canopy architecture. And then we look at just, I mean, there is less data on this, of course. For maize, there is a lot of data. But if you look at the different grasses, here we did a review looking at annual ryegrass, hybrid ryegrass, oat, perennial ryegrass, rescue grass, timothy grass, and wheat. And you look at the parameters of the model, and the parameters of the models are very similar. So when we compare the dilution curve for parameters of the model A1, A2, or using the past AB, we found that the parameters of the model, they did not differ. Of course, in many situations reveals that uncertainty, because in many cases the data or the data quality not the best, except for wheat, probably. The level of uncertainty is one of the things that we need to start discussing and talking about the number of studies, number of samplings, number of fertilizer rates, number of observations within a study. When the number of data is small, sometimes we are seeing that the determination of the critical curve has a large uncertainty. And of course, for example, the study from Gilles LEMAIRE is the exception because I will say that it's good data quality. So not always small data sets are problems. The problem is that in a small data set, we might have higher chances to get bad data or something that it will be hard to be overcome if we don't have a large data set. We also look at drought. I mean, because we start wondering, and Gilles brought me into this too, and then we look for, with another researchers, we start looking at the effect of drought. And we look at this, an example of one of the papers published a couple of years ago. We took data from multiple sources, but believe me, when we start looking at data, this is something to tell, from many countries, it's really hard to find data that it has this level of detail, what I'm showing here. It took us a lot of time to find data sets that they were published, that they have like a biomass N uptake, where we can calculate NNI, and also, in addition to all these, evapotranspiration measurements. And we here, to explain a little bit, we have maize in dark symbols, we have sorghum in the gray symbols, and we have irrigated full symbols and rain-fed open symbols. So, and we have different supplies. The circles are high and low nitrogen. So we calculate the natural nutrition index. Of course, in many situations, as expected, in sorghum was higher, and in maize was a little bit lower. And then the evapotranspiration was the same. For maize fertilized, higher evapotranspiration as compared to sorghum because of the yield potential. The most important aspect from this research is specifically looking at this graph or rethinking on connecting nitrogen uptake to transpiration. So if we need to start working and developing concepts of how we start connecting and quantifying well the effect of water, we need to start thinking about measuring these elements. I mean, nitrogen uptake, and here we show that depending on the situation, see, the first panel A is with really high fertilization, the panel B is with lower fertilization. And then in summary, what happens is, for us, this nitrogen uptake transpiration seems to be a really good way to combine these two traits, the nitrogen and water use. And the arrows represent the basically effect of the deficiency. And we have a very high reduction of uptake. Most of that reduction for maize is substantial. So maize is extremely susceptible to deficiency. And we will discuss a little bit about this. This is not something that it came by chance. Maize has been bred for high productivity, high yield, but high adoption of technology. So when we have a nitrogen deficiency situation, it's the one that is the most penalized. And we have a high reduction, as you see on the first arrow one. And then when you look at the reduction of N uptake, we have the second arrow shows the reduction of N uptake that is due to the reduction of the N supply, specifically separating these two factors. The one that is a reduction of N uptake coming from the water deficit, and then the second one that is a reduction of N uptake that is coming to reductions of the availability of nitrogen because of the lack of water in the soil. And we were able to come up with this nice, I think that from my opinion, indices also looking at combining water stress And then we were comparing the National Nutrition Index with National Water Index. And this National Water Index were able to show, using some of the data from maize and here in France, the allometry between uptake and transpiration. And then the point that we need to compare things at similar biomass. I keep emphasizing this because I have seen situations of people trying to compare transpiration or water use efficiency, but comparing things that they have completely different sizes. And that's a problem. And then what you see here as a summary is like we have a situation on these points on the upper section where we have an excess of nitrogen, so we have a higher uptake relative to water transpiration. And then we have the second point here below the line, that is the 1-1 line, which is the water deficit that has a large impact on basically the plant nitrogen nutrition. So these are the concepts when we are thinking about water, but think about that we still haven't explored too much relationship of nitrogen with other nutrients, right? Sulfur, potassium. So start thinking about that. If we start thinking about doing co-limitation studies that they are very simple, a factorial. I have nitrogen application at 0, medium, high, and I have maybe phosphorus application. How do I combine these two effects? Here is an example of looking at combining two factors and looking at if the effect is coming from the reduction of nitrogen or from reduction of the other factor. So the summary of drought is basically, it's a very complex process. Everything is really highly connected to this allometric between biomass and water, biomass and nitrogen to water. We have a direct effect of water on growth, and this is an indirect effect of this water restriction on soil nitrogen availability and the lack of uptake. And in many situations, we demonstrate that this effect indirect and drought on nitrogen availability applies to both, to maize and sorghum, but we tend to see in many situations, as expected, that for maize is much, much relevant because of the susceptibility of maize to deficiency, to nitrogen deficiency. So based on that, we start thinking about, okay, is there any effect on drought if we compare different critical dilutions at the different irrigation levels? And this is not a closed question, okay? We did a study. Gilles was also helping and framing this idea. And it took us some time to really work on this data set and this paper, because when we compare rain-fed versus irrigated for maize and wheat, again, one of the main issues is that it's hard to find good data sets. And everything goes back to still we need to do research, and still we need to do basic foundational research. This critical plant ecophysiology research and measuring temporal sequence of nitrogen uptake, water transpiration. So in this case, if you look at these specific studies, an example for rain-fed irrigated, we haven't seen using Bayesian model difference in these two curves, but the problem also is that we are seeing that the rain-fed curve has a very large uncertainty, which basically is telling us that when we are under deficiency, and maybe when we have under extreme drought deficiency, it's really hard to quantify this critical dilution curve. And then we need to find ways of improving maybe the data collection, increasing the number of sampling times on the data collection, and testing this approach with a different level of stress. If you look at these data sets, probably they don't reflect a high water stress levels yet. So the question is, how do we use National Nutrition Index? And I think that this question is probably not too valid for many people in France, because many people, since they are very young, they learn about the National Nutrition Index. I'm still puzzled seeing that in many situations in the US or around the world, it's known, but it hasn't been used. So I will show you an example of what happened to maize in the last 10 years very quickly. In the last 10 years, and maybe I'm guilty of charge on this, because one of my review papers when I did my PhD long time ago, 10 years ago, I mean, we demonstrate that the new maize hybrids, they tend to uptake more nitrogen post-flowering. And because of that, everyone started thinking, oh, that means that if I apply nitrogen post-flowering, I should be able to get a lot of responses. So after these 2 papers that they show this change in increasing biomass post-flowering and more uptake, we start seeing a lot of people thinking and investing money and resources on, let's investigate application of nitrogen late season. And this was overall, we are seeing increase on 30% of post-flowering and uptake on these modern hybrids when we compare them with the old hybrids. The main problem is when you look at the literature, the scientific literature from 2012 to 2020, there were many studies after this review paper. And all the studies, they try to link post-seeking and uptake. But the problem that, I mean, the concept was simple. The concept was, oh, if we increase synchrony of applying nitrogen with the plant demand, we will increase efficiency. The issue was this, that many people were starting to find that was not that simple. There were many studies, and these are real cases. People apply nitrogen close to flowering, at flowering, a few days after flowering, and they found this. They found that in some situations they see positive responses, and in some situations they see negative responses. And they start kind of wondering, is this something that we can use with farmers? Can I tell to a farmer, apply nitrogen and you might get a response as an answer? And then we went to this topic and we start thinking about nitrogen nutrition index. And then we started doing a review. This is the best way that we know how to start doing things. So we start looking at all the studies that got published in that 10 years, almost 2010, 2009 to 2019. And we divide the data set into what we call early nitrogen application until V6, and then late nitrogen application until after V6, when maize was with 6-leaf stage. We compare the rates just to make sure that we were using similar rates. So there was not evidence of difference on rates. And then we did a meta-analysis, which is very popular. It's a statistical technique. Some people might say very sophisticated. It's very sophisticated more when we don't know exactly what we're doing. Mm-hmm. And when we do the meta-analysis, the conclusion of the meta-analysis was, in overall, there is no response to application of nitrogen late season. And then my PhD student at that moment was saying, okay, we finished the paper, we're done. And I was not too happy. I was like, I think that we are missing the message of the paper. So I asked specifically, I bother my students a lot, and I came back to his office and I say, what about if we look at only the studies that they have N uptake at flowering? And then we can calculate nitrogen nutrition index as an indicator of deficiency. Of course, when we look at all these studies, there were just a few that they have N uptake at flowering. And then, voila. When we were looking at the data, we start looking at relative yield, and then we calculate the nitrogen nutrition as silking. And then what we start seeing is that, as already reported in many other papers, seems to be a critical threshold around 0.9. And then it shows that if you are below this number of nitrogen nutrition, you have a high level of response. If you are above the number, your response is very unlikely. But then we took another step, and then we look at, since we have all the data, we look at if there was any relationship between nitrogen nutrition and post-silking and uptake. Because we hypothesized that if the post-silking and uptake was larger, it's because we have deficiency earlier. As simple as that. And then we start looking at that, and you see the panel B there, and it shows that as we start seeing deficiencies, the relationship is going up, and it's going up more clearly. And we have in some situations close to 60% of the nitrogen coming after flowering, and in those situations was with the nitrogen nutrition index was extremely low. So the nitrogen deficiency was linked to the potential for an uptake after flowering. And after we did this, we divide the data set, very simple, in 3 sections. low post-silking, medium post-silking, and then high post-silking uptake. And then once we did that, we start seeing that the group with low post-silking uptake didn't have any response to application of late nitrogen. The only response that you see on the panel to the right, to the left, is similar yields, but in fact the late nitrogen application seems to be penalized, and only we have increase of grain concentration protein. In the right, we see that those that they have large N uptake post-flowering, we see an increase on yields, and not only an increase in yields, but we see an increase in yields that is with less nudge, applying less nudge, increasing the efficiency of using that nudge. Here is an example. Now the problem is, how do we include NNI in our diagnostic tools? Because every people is doing nitrogen applications late season, but they stop doing it because they see erratic responses, okay? And then switching a little bit, and we will go back to this topic at the end on the decision tools. We started discussing with Gilles also this concept of breeding for nitrogen use efficiency. It's a very critical concept from my side, but again, when we start looking at the maize data set, we start seeing that something is not looking well. And why I'm saying that is because if you remember the study that we investigate looking at drought, we are seeing that in that situation, the sensitivity of maize to deficiency is really high and extremely high. Compared with sorghum is quite large. And then the question is, unintentionally, while we were improving yields for maize and increasing the adoption of fertilizer and technology, we might also unintentionally increase the susceptibility of maize to deficiency. Okay, and what we are showing is this situation. We are showing that breeding for high biomass, breeding for high yields, what we breed in many situations for many crops, it basically take us in the direction of applying more nitrogen, moving the direction of applying more nitrogen, and what we are doing is increasing the environmental risk. And then if you go to the opposite way, like this year, the problem that we are facing of scarcity on resources, natural resources, and high prices of fertilizers put these crops into scenarios where they are highly susceptible to deficiency. So the hypothesis was that increasing the fertilization for modern hybrids help us to attain yield, high yield, but also increasing the dependency to fertilizers. And also, I mean, while we are increasing that dependency, we're increasing the environmental risk. And we can mention that and we can validate that, because I went back to, and this is one of the things that we discussed with Gilles, and it's impressive that you finish a PhD and then you still can use the data from your PhD. So we went back to, I went back on time 10 years, and then I look at the data from my PhD, and then yes, when we summarize on this study, on this review paper, close to more than 100 studies for maize in the entire world. And then what it shows is yield in the new hybrids increase with fertilization. And the increase is much larger. So if you look at the gap between fertilization, the red points versus the blue points, the gap is much larger as we are increasing the fertilization rates, okay? And unintentionally, it seems that we did something on the lower end. When we were not applying nitrogen, it seems that we minimum, but very minimum, we increase very, very slightly the yields on the modern hybrids, okay? But very small, very small. I mean, and in many situations, I will show that it's obtained with a high susceptibility to deficiency. Not only that, that in this graph, using the same review data, we show that if you look at the NNI at flowering, we were able to achieve in the old hybrids an NNI of 1 with less nutrient application as compared to the modern hybrids. Not only that, that this was the first time with Gilles, I think that we put together another data set too, and we were looking at not only we are increasing the dependency to fertilization, but also there is something very interesting. When you look at the old versus the new hybrids, and you look at without nitrogen and with high fertilization rates, just looking at the two corners, we haven't changed the nitrogen nutrition index. We haven't changed the nitrogen nutrition index. And I think that is because we have been focused specifically on breeding for high biomass and yield. Not only we haven't changed the plant, we haven't changed the ER concentrations of NNI. So we need to start thinking about a new framework. The old framework that we discussed in another paper was yield versus end supply. And this is what took us here. The last 100 years, we always start talking about what is the optimum rate? It's 100? No, it's 101. No, it's 105. Oh, wow, excellent. No, it's not a linear model. It's a linear plateau. No, it's a quadratic model. The R square is better. It's a quadratic. So we need to get away of these conversations and start thinking about how we can compare things. And then one of the ideas that we start working with yields is looking at these expressing relative yields. So if you see here on the right panel, we have yield divided yield max, maximum yield for each location. So relative yield. In fact, we can do the same with biomass. I will show an example. And then the NNI. And then if we have data from the entire season, we are proposing to use the integrated NNI. We'll consider different moments in the season as a reflection of not only one point in the season, but different points. And this is just to get away from NUE and recovery efficiency and conversion efficiency, okay? Because these are all static indices. They are not giving us information about processes, okay? And everything is trying to think about how we can compare different environment, different scenarios at similar biomass level. So this new framework is proposing this idea. It's trying to think about how we can calculate and think about in relative NNI integrated and relative yields and start comparing different scenarios. And if you want to have an idea how to use this framework, the way that you can use this framework is very simple. One example there is if you look at the G1 and G2 in the graph, you will see a situation where G1 is a genotype 1, G2 is genotype 2. We are increasing relative yield, but we increase relative yield by increasing the NNI. So that will be the optimal scenarios where we are doing both. We are increasing yields, but we did that by increasing the NNI. We are increasing that nitrogen efficiency. Second scenario is if you compare G2 versus G3. So in that case, what we are doing is reducing the NNI. So in this situation, we are maintaining yields, but we are reducing the amount of nitrogen in the plant, okay? And this is another scenario that could be beneficial in the sense of, maintaining yields, but potentially increasing that efficiency and using less nitrogen. And then if you look at one of the last combination is the G4 and G3, which basically means that we are increasing yields, we are increasing the utilization of nitrogen with similar NNI. And let me give you an example, because it's easy to propose a framework, or maybe not that easy, but we were able to give an example. So we just finished a study, and we look at data sets. In fact, we look at 3 data sets. There are 2 data sets that came from my team, and there's 1 data set that came from another publication. So in this case, we are looking at 3 data sets, 1 for maize, sorghum, and spring barley. And they are all historical, which means that they are using hybrids or genotypes from the 20s or from the 60s or 40s, all the way to new. As we discussed in many situations, and if we want to publish a paper, we just can publish this figure and saying nitrogen use efficiency increase over time. And everyone will be happy with us. We are much better. We have increased nitrogen use efficiency. We increase the yield with the same or similar amount of fertilization. However, when we think about NUE, and we discussed about at some point in the presentation, this NUE is highly influenced by yield. So in many situations, we cannot separate NUE from the yield progress. And it's hard to untangle this progress on an NUE when you are looking at this progress on yields. So we divided these using the traditional coefficients: recovery, conversion, and harvest index. And what we found is that the main aspects that we've seen increases are in the recovery and in the harvest index. So recovery seems to be going up in maize over time, and similar situation is for harvest index, and similar is for barley, and then lastly for sorghum. So the changes in the conversion efficiency are kind of very minor at this over time. But again, is this the best way to calculate and to demonstrate the progress of nitrogen use? And we went back and we say, let's look at NNI. And then we calculate the integrated NNI. And then what we are seeing here is for all these three crops, we are seeing that in fact the integrated NNI over time during the last close to 100 years has not been changed, confirming what we discussed in the past for maize. So now we have a confirmation that has not been changed, in many situations even decreases slightly for barley and sorghum. And then if you look at the framework here on the right panel, we are basically using the framework and showcasing how we use this framework. We calculate, rather than calculate relative yield, since relative yield is influenced by harvest index, so we try to remove the harvest index effect, that the harvest index has an effect over time, and we are only looking at relative dry biomass. And then we are looking at relative dry biomass versus integrated nitrogen nutrition index. To simplify, because there are many, many points, we try to use all the experiments. What happens is for maize, basically the old hybrids with under fertilization, we are basically going from old hybrids all the way to high new genotypes. We are maintaining NNI, increasing relative dry biomass. Okay, so maintaining the NNI and increasing biomass. For those hybrids, when we look at under deficiency, we are seeing that we sometimes increase biomass, but the NNI is going down, which basically confirms that these new modern genotypes under without nitrogen, I mean, basically they are more susceptible to N deficiency. And if you look at barley, it's very similar to maize and very similar. In fact, in barley, we are not even increasing biomass, we are maintaining only biomass, and then it's more and more susceptible to deficiency with lower NNI. If we look at in sorghum, it's different, but sorghum has very low improvement, so it's kind of one of the last in terms of the progress. If we focus on this analysis, we are looking at yield improvement only was possible maintaining NNI and showing reductions of NNI under deficiency. And in fact, these are the first, I think, findings that help us to understand that many of the nitrogen gains were extremely unintended under nitrogen deficiency, but it shows that we have really lack of progress on reducing this dependency to fertilization. Okay, so we still have a high dependency, specifically more on maize, to nitrogen fertilization. To start closing the presentation, we also start looking at this one paper that came out last week. And we were able to confirm a hypothesis also that was formulated by Gilles LEMAIRE. They formulate, if you look at that figure, and many of you probably are quite familiar with this figure, and basically it was postulating that reaching NNI at 1 when you have silage maize, higher NNI when you have flowering. So it means that we are creating a reservoir, nitrogen reservoir pool. And then we have a study that is a new maize hybrid. So it's still not out. But this hybrid, what it does is increasing the transcriptome and increasing a protein expression, that what basically is being reflected into increase in nitrogen uptake at B11, okay, and is reflected to increasing the nitrogen that is stored in lower parts of the canopy, stems. And then basically what occurs is after this process is done in the plant, that extra nitrogen starts feeding the reproductive. Even on the moments that we are seeing that during the reproductive, that the nitrogen availability after flowering decrease, and in many situations connected also with some reduce of availability of water, so connected to some level of stress, and also usage. The crop use most of the nitrogen, soil mineralization, nitrogen coming from soil mineralization, and the root capacity for taking up nitrogen is declining once we start with the senescence process. And what basically shows is that if you look at the different treatments with and without nitrogen, we have a situation of zero nitrogen and a situation with high nitrogen. In all the scenarios, we have two hybrids. We have one that is the wild type, gray bars, and the color bars are the genotypes that they are expressing this trait. And what we are seeing is in all the situations, in B11 specifically, we are increasing the uptake of nitrogen. And we were able to quantify this by using isotopic label studies. So the question is this the right path for increasing yields? And then what we are seeing is we are increasing the uptake, increasing the assimilation of that nitrogen in leaves. Because now what we did is that we changed the amount of nitrogen per unit of leaf tissue in the lower part of the canopy. So we basically use that lower part of the canopy as a reservoir of nitrogen. And to demonstrate this complexity of the process, this is a figure that we include on the paper. And the figure shows that most of the changes occur before flowering. And then after flowering, what happens is just like a cascade event. That nitrogen is being used, is being mobilized to the ear, and then we are increasing the harvest index, and then reflecting that in some situations, that mobilization into increase in nitrogen concentration. And then when you are going to the field, you are seeing the difference in the canopy. You are seeing that one canopy was a little bit more open, and the other canopy was very dense. So we were seeing some difference basically, and dark, very dark on nitrogen. So which basically, I mean, visually confirming this effect of nitrogen uptake. So we have potential to increase opportunities for future and increasing specifically yields based on nitrogen use. To finish, and then when I get the question in many situations, when I visit many places this week, why I decided to come to France. Besides that it's nice, and besides that my great relatives were from France, one of the big things that I'm thinking and opportunities is start expanding the global network and trying to think about how we can think together. And in order to do that, I offer the time of many of my students and even the time of myself and then Gilles and David. And we put together one publication that was to release data. That was the idea of this publication. And this publication also came out last week. And then the publication, what it does was a review that basically what we did is that we would try to collect all the data that was available and ready, share, establish a protocol, and then do a systematic review and trying to open a new database on nitrogen nutrition index for multiple crops. If you look at the map, we collected data from multiple crops. I think that we have close to 19 total, 36 papers, close to more than 4,000 observations. And then it's all the dilution curves for all the different crops. So this data set is available, so everyone can use it. And I hope, as a part of this visit, is that we can expand the data set and we can try to collaborate with more people to see if we can add more data. And these are some of the ideas. Josefina is working on this right now. She was very afraid of showing this figure, disclosure. She did that I think that during the plane or on our travels, but it's an example of saying, how can we start using this data? This is coming from the review that we just finished. We didn't put this figure in the paper, but this is an example of ideas for the future. This data set really can help us to guide how we can collect dilution curves, how we can stop this madness, if I call it some way, of doing dilution curves everywhere in the world, in your garden, behind your garden, in front of your garden, just to check if it's different. And then how we can start focusing on what is next. And questions like this one, for example, is the critical threshold for National Nutrition Index the same across all crops? Or depends on the leaf morphology, or the plant morphology, or the canopy architecture? And we don't know that. I mean, I think that we need to start thinking about ideas on how we can start using these data sets. Testing the universality of the dilution curve, thinking about how we can use this information, okay? The main goal is to open this data set and create more collaborations. And this is an example of this idea. And to close, Gilles didn't see this one because this paper got accepted this morning. We also put a new study that is coming out probably in the next week to create some guidelines. And I appreciate maybe some of the comments from the anonymous reviewers because they were very helpful. But we tried to put a paper we did a synthesis analysis. We look at all the specific criteria for establishing the dilution curve. And then we look at basically studies that they have different number of experiments, different number of fertilizer rates, different number of sampling times. So I always ask myself this question in the past. I need to design a new study on critical dilution next year. How many fertilizer rates? How many timings I should be sampling? How many timings, how many genotypes should I use? So we look at 5 different points of the data sets: number of studies, number of fertilizer rates, number of sampling times, number of times that the data reach the plateau, and the precision of the studies. And we use the Bayesian model. So a big short summary, because this is very fresh. The number of studies that we collected in the data set was one of the main factors affecting the uncertainty. So basically telling us that if we can capture more environments, sometimes it's much better to give us some information on the uncertainty. As we discussed in the past, we confirmed that 3 fertilizer rates are kind of the minimum. And then in some situations, it makes more sense to increase the number of sampling times than the number of fertilizer rates. So that's something very important as a good outcome. And again, the idea of this paper was specifically looking at how we can establish some guidelines for defining dilution curves. I mean, even dilution curves for some crops that we don't have dilution curves. I mean, I discussed yesterday with some collaborators from Dijon. We have some crops, I mean, like soybeans, that we don't still have a dilution curve. And many people were surprised on that. But this is an example of how we can start establishing and thinking on that. So to finish, this comparison of NUE across cultivar species must be done in similar biomass. Think about the water status. Think about the influence of other nutrient limiting factors to avoid confounding effects. From my personal opinion, I want to be, or potentially I would like to write a paper maybe, to be out of the NUE. And I mean, it was a good ride. We have a good fun times using NUE and then recovery and then conversion efficiencies, and maybe are relevant for mathematical processes, for agronomical processes. But when you're looking about decision support tools or selection for breeding, they're very static and could be very misleading. think about limiting factors. I mean, we talk about drought, but think about all the soil nutrients. The effects are similar. No, drought has a direct effect on growth, and then reduce the ability of the plant to growth, and then reduce the ability of the plant to uptake nitrogen. But there is an indirect effect of drought also connected to reducing an ability of that plant to capture nitrogen because there is less nitrogen available in the soil. And then the summary of our presentation here today is thinking about how we can start moving to this new framework, how we can start working with more people and trying to move away from the old traditional NUE and thinking about how we can integrate NNI and soil nitrogen as another factor in the decision support tools. From my opinion, and this is what we need to do, and this is one of the efforts that we're trying to conduct, and the purpose of this trip is really thinking about transdisciplinary approach. Today we're working with an agronomist, and we're working with statisticians, plant crop ecophysiologists, breeders, farmers. So really thinking about how we can develop larger teams, more international teams, to try to isolate research disciplines. I mean, to reduce that kind of a barrier that we have in people working in silos and trying to get us connected in this. And this is the main goal for establishing this global initiative. So as I always say, the secret from our team is the team. It's very simple. And then people working all towards one goal. And I can say that I have a large pleasure to train new people and young people. So that's, I hope that we can have more collaborations. And then like one of my students is here today. She's doing an exchange here with Debbie Makowski. So hopefully we'll have more opportunities for exchange students in the future. With that, I will finish here. I will thank you for your time, for listening, and for being patient this morning. I hope that we can spark new ideas and questions. And then I will leave this presentation. I think that everything will be recorded. So, and if you are interested on the papers that we discussed on the presentation, so I also put a list of some of the papers, and I have all the list of main papers that we discussed today. So this presentation will be available. And if you need to get access to any of the papers that we have discussed today, feel free just to send me an email. I mean, there is my contact information, and I will be more than glad to share those studies with you. Okay, I think that I will stop there. Thank you.
Thank you very much. Thank you very much, Ignacio, for this very complete conference where we have the topic about both agronomy, plant breeding, and crop physiology. It's a pleasure for me to hear this very interesting speech. And just before to give to ask people to have a question, I just want to give two important messages. First is that we have to consider plant as an allometric system. And as we are educated in plant physiology or in agronomy with using the metric of ratio. But the ratio is totally inefficient. Is not, for plant, either allometry is driven the plant development. So we have an effect of size. And we have exactly to do the same revolution as animal scientists when they discovered that to express the physiology of animals of different sizes, they have to use the metabolic weight concept. So the nitrogen dilution is not other things than the metabolic weight of the plant. And it is a totally revolution in our mind, is exactly when we go from the flat earth to the spheric earth. So it's the first messages. So we cannot compare any different plant if you don't take into account they're different in size. I have forgotten the second messages, but the second messages is all the elements all the factors are deeply linked. So we have observed that yes, nitrogen is important, but very soon you have to use water status and also to use phosphorus status and so on. So we have to link together these different. And what I want to say is also that to monitor plant and status and to report plant and status in any agronomic experiment is also necessary as to report weather or climatic condition or soil condition. We cannot express anything in whatever we compare in experiment if we are not able to say at which nitrogen status was the plant. So now I have a long career of reviewer in for different papers, and a lot of papers are giving excellent data, excellent about anything, but never the nitrogen status of the plant. So please now we can open the discussion with people wanted to give the first to people outside, Marie-Hélène, or everywhere, every other people. Do you want to ask a question?
Well, thank you very much, Ignacio and Gilles. I am pleased to welcome you and to discuss with you. And thank you very much for your interesting presentation. I have a few questions. Well, the first one is about the price of fertilizer, because you say that it is important to take into account the price of fertilizer in determining the best fertilization to apply to a crop. But very often, I agree that the price is highly variable, but the problem is that very often we know, or farmers know, the price after the period of fertilization. So it's not so easy to take it into account in determining the fertilization. I have two other questions. Maybe I ask them, and after I let you answer. The second is about the way to consider other factors. As you mentioned, water or phosphorus are important factors to consider also. But we have also another main factor to consider is pests, because now we have to manage the crops, if possible, with a high reduction of pesticide use. And pests will interact with nitrogen status and nitrogen functioning of the crop. And so I wondered how you take that into account. And this is, it makes the link with my third question about models, because you stressed the importance and of models, of using models, and yes, in order to manage fertilization, but very often models do not take into account all these factors, and mostly pesticides are not taken, or pests are not taken into account in models. So don't you think that the use of models to think or to manage fertilization has today great limits? Thank you very much.
Yeah. Well, first of all, I mean, it's a pleasure to put a face to some of the articles that I have read from your site. So very, very, very good researchers. So appreciate to have this conversation. So very good questions, as I expected. Nothing less. Let me start with the first one. You are right. Completely right. In many situations like this year, for example, if I give an example what happened in the US, let's go back to October 2021. Many farmers, they were like, well, looks at the price of the commodities are going up, everything seems to be fine. And then some of the people that they were able to apply fertilizer immediately after harvest, they got it right. The people that was not able to do that, like they wait a month or 2 months, they pay that fertilizer 2 or 3 times more already. And the people that they were waiting until February, which many of the people, they apply the anhydrous ammonia, no? In the US is very popular. They were paying that 5 to 6 times more. Yes. And then the consequence today we will face this year is that most of the corn or maize that we have in the field in the US is not under optimal nitrogen conditions today. And in fact, we're looking at that because we are trying to see how we can collect some of this information, even using some satellite data, remote sensing. So, but it's like that, and it's a problem. And the question is, it's hard to predict. I mean, I would say not even hard to predict, it's almost impossible, because if you think about what happens to the weather, it's exactly the same. If we want to make predictions for weather conditions for 2 or 3 months, I will say hardly we can predict what happens next week. Imagine if we want to make a forecast for 2 or 3 months. So what we start doing is start thinking about this idea of what if we use historical data? What if we use historical evolution of changes on prices? What if we use historical weather information from the last 50 years that will give us a sample of the variability? And basically today we are trying to focus on developing or working on developing decision support tools that will include the historical variability. For example, on this study that I show in the conversation, in the presentation, what we did on the fertilizer crop price, we didn't use the average. We include this factor as basically a distribution of the ratio. So we include the historical data. And trying to look at, yes, it's more challenging, but that's why we work, or we are training new people on using Bayesian or using posterior, distributions, and thinking about how we can connect historical information so we can provide to farmers scenarios. And we can tell to the farmer, before he decides the fertilization, if you apply, if your fertilizer price is here, this is your revenue. If your fertilizer price is here, this, and so we're trying to provide all the different scenarios possible. And then we leave the farmer to take that decision. But we also kind of emphasize the point that it could happen because it happened in the past, and you can see that by studying this natural variability, you may most likely will be on these kind of fluxes. It's always a case that, it happens, and I think that it happens on purpose sometimes. Commodity prices are going up, fertilizer prices are going up. Anytime that the crop prices are going up, the industry is saying, oh, these farmers, they have more money. let's start increasing the seed cost, the fertilizer cost. So there is a correlation. And if you look at the past, it's there. It's all the time. So then going back to your second point, excellent question. In fact, I will disclose I'm not an expert on pests. I'm not considered to be an expert. It's good to have limitations. And I have some ideas. In fact, yesterday I was in Dijon and I visited with one professor there at Delphine. And I was very intrigued about the way that they are using or connecting the dilution with competition with weeds. And for me, that is one of the, I mean, that is the evolution of how we can move into considering multiple factors, okay? And in fact, one of the things that I was doing when I was coming to the presentation with Gilles, I was discussing about one of the things that we might need to do with NNI is to think about the idea of not expressing this as a biomass, but to see if we can move to leaf area. And if we move to leaf area, then we will be accounting much better for example, insect defoliations. And then I think that this will be the clear connection between evolving the NNI into this nitrogen biomass into something that could be nitrogen leaf area evolutions, because that will help us also to do much better predictions also using remote sensing with sensors. So, and your last point on the models, yes, I think that the models have a lot of limitations. A lot of limitations. And I usually try not to marry to any model. In fact, I'm open to test as many models as possible. And then one of the things that I was trying to look, thinking about how we can model competition or how we can model disease influence or pest influence. I think that in many situations, if you want to model that, the easy way to model that is via leaf area, evolution of the leaf area. But I'm with you. I think that the models, from my perspective, at least even from my part of the training young people, for me, the models are an excellent exercise to unify all the complexity. That doesn't mean that is solving the problem, but makes the students and young people to think about more about other factors. Because there is some people working on only, my research is about nitrogen and maize. But what about pests? What about disease? What about, and then unless you start using this data into connecting the data set with soils variability and effect of soils, weather variability, and then start connecting with other factors of a farming system, no? And not even thinking about, in many situations, we are only discussing about one crop at a time, but even thinking about, we have a new paper that we just finished a month ago. We talk about this legacy. What happens when you move to one crop to the next one? And what happens to this nitrogen? And I think that we have even less information on rotation effects or system effects, or even if we introduce a cover crop or a legume, no, into the system to increase efficiency. But I'm looking at the models as a way to trying to simplify the complexity, but understanding all the limitations. And then my most important message when someone is working on models is, unless you're a good crop ecophysiologist, then you're not a good modeler. I have many people that I know that they are good crop modelers, but they are awful ecophysiologists. And the problem with that is that they touch the model without knowing what they're doing.
Model are sometimes very useful to identify our lack of our knowledge.
Yes, I agree. Yes. And did you, maybe I have a last question, did you also analyze the practices of farmers around nitrogen fertilization? And do practices of farmers, their variability, or I don't know what, can lead to new questions for you?
Yeah, in fact, we have one study that we conducted 5 years ago. And in fact, I don't think that we finished publishing yet, that one. But we were looking at a field condition on a farmer field. And we captured data from multiple points of the field to demonstrate to the farmer that even on the National Nutrition Index, there is variability in many points on the field, that many of that variability is coming connected to soil and weather information. So there is a spatial variability. And the main point is to demonstrate, or at least to discuss with the farmer, that if you are thinking about fertilizing, it's easier to think about fertilization when you are understanding that you have variability. And then more now than ever, we need to start thinking about, if we want to also at the farmer scale increase efficiency, we also need to start thinking about how we can help the farmers to apply nitrogen in different ways, in different sections in the field, and basically take into account this spatial variability. Okay, and I think that many of the models today, they don't do it, or they derive the variability of yield coming from yield, of the variability of nitrogen that is coming from yield, and in many situations it's not a linear relationship. So that's a problem.
Can I have just not a question, but perhaps a reflection about the big change, the big revolution about the agronomy has been established long term ago by field experiments with block and calculation statistics. But in fact, this system was a system to put the dust under the carpet. We put all the good information in the bin, in the residual, and to study the isolated factors.
Of course, yeah.
By the means of use of diagnostic in field diagnostic in plant, in situ, perhaps we don't need to have a sophisticated split plot design. We can use only covariable with recording the maximum information about nitrogen status, phosphorus status, sanitary status, whatever, in a local, and to have a more spatial, instead of to have a very fixed system where the more important information is not apparent.
Yeah.
I think we have at this turning point by using satellite, using spatial data, and very well diagnosis of different factors.
Yeah, and then maybe to add quickly to that is like, I mean, sometimes we are thinking on these ideas, and then what we are doing is more observational studies that you basically collect data from different points in the field, and then what you do is that you describe all the information that you have. So you describe the plant biomass, because we need the current plant nitrogen status, and we collect the soils to basically account for what is expected to see or to come from the soil in the next coming weeks, and trying to think about, and then use the weather, use the other soil properties to think about how we can start developing these tools. I will still think that the development of diagnostic tools is not something simple. It's easy to say that, or it's easy to preach about doing that, but it's not that easy to put it together. In fact, many of the decision support tools that we have today, even the ones that they include remote sensing, satellite, or in many, in my opinion, they don't have a foundational research behind it. Many of them, they have a linear relationship between NDVI and how the plan looks today. And I'm really mad to see that we went away from doing sometimes also this traditional basic foundational research. We focus so much on the cool and the new things and everything that is concerning the funding, no? Where is the funding going? Contamination and losses, no? But what about how we can predict National Nutrition Index using a proxy, no? A sensor? Or what are the leaves, no? The leaves that I need to look in the canopy. Is there any way that I can avoid harvesting the entire plant? Can I use other sections of the plant as a proxy of National Nutrition Index? And how well these sections connect to satellite or to any sensors? Because, I mean, I think that we are always going 10 steps behind. We are always, the technology is coming out. We have the satellites, we have everything, and people start saying, oh, look at this. I collected 1,000 data points. I look at linear correlation, and now I'm seeing that NDVI predicts R squared 0.9 the variability of these fields. And basically, we're not doing science for me at that point. We're just basically doing mathematical models and in fact, simple mathematical models, 4th-grade mathematical models. And then we forget about the science. We forget about what are the things that they really make us to be better. Like, I mean, and then going back to the basics. What are the best timing in the season to account for National Nutrition Index? What are the best spectral bands that we should be using? What is the best type of sensors? I mean, I'm sensing the upper leaf, or should I sense the 2, 3, or 4 leaves in the canopy? Does it change with the architecture of the canopy, the type of crops? And all these are relevant, extremely relevant, foundational plant ecophysiology, remote sensing, however you want to call it, questions that are not being addressed today. That we just have a sensor, a cool one, a new one. Oh, look at us, a new hyperspectral sensor. It shows that I can predict in the night. No clue how, but the questions are linear. And we don't even know, does it work for Argentina only? Or if you take it to France or to US, it's entirely different. And I think that the problem that we don't know is just because we are not thinking about universal or foundational research. We are thinking about just sometimes going quickly to the decision tool. Too quickly, without thinking about the science first.